Okay, welcome back, and we'll continue with Joe Osborn from BNL. Who's going to tell us about calorimetry and tracking. So, Joe.
Good morning, everyone. So I'm Joe. I'm going to talk to you about calorimetry and tracking, which I know you've heard a little bit about already. So I will discuss more generally some of the points related to calorimetry and tracking, how they apply to many different experiments, not just, for example, EPIC, you'll see common themes in my slides over the next couple of days from the SPhoenix EPIC experiments, as well as the ACTS software collaboration. We'll talk a little bit more about tomorrow. Okay, I lose my clicker.
Sorry, click on this. Yeah.
Okay. So I just had a new baby 3 months ago, so I wish that I was dreaming like this one was, but alas, I am not. Suppose you were dreaming as nicely as this baby is about someone who gave you a pile of money to build a particle physics experiment. And you got to design something from scratch, like, for example, the EPIC experiment. So what I'd like to ask you all is, how would you go about it? What questions would you ask, and what would motivate your choices? I'm curious to hear your thoughts. And if you don't have any, that's okay too. But I think these are the kinds of things that you should think about. For example, in the discussion sessions tonight, I think you should consider what kind of things would drive your choices. Maybe you'll dream about it tonight. So there are a couple of things that I think are important to consider. So the first is probably the most important, the physics measurements that you actually want to achieve. If you want to measure some physics process that's has a photon in it, better build a detector that can measure a photon in the energy range that you would like to make your physics measurements. So this is probably the most important factor in designing your experiment. But there are many other factors that contribute to this and that play an important role. For example, accelerator conditions. Maybe you have some space constraint based on your accelerator complex. That means you have to build a detector in some particular area, some particular unit of volume. So it can't be really big or something like this. Maybe your accelerator has really high luminosity, so you expect that you have all sorts of background particles from things that come way down the beam pipe. How are you going to measure your photon to do your physics measurement if your detector is also measuring thousands of other photons that are completely irrelevant to your physics process? You should also think about mechanical constraints. As a physicist, you can say, I want to build a beautiful detector like that baby was just dreaming about that will do all of my amazing measurements. And you might take this to an engineer, and that engineer would laugh at you and say, this cannot be built in reality. You have to build something that actually can physically exist. So there are, of course, engineering constraints. And then also very important in our business is cost and schedule. If you do not have an infinite pile of money, as much as we might like to dream that we do, that will never be the case. So you have to build something that is within the amount of money that you are allotted, and you have to build something that you can build in a reasonable amount of time. If you want to build a detector for the EIC, you better be able to do it with technologies that we have now that can be built in the next 8 years. Building some calorimeter or tracking system that needs 20 years of R&D is not going to do you very much good for an EIC. So all of these things are important. Okay, so let's talk about modern particle physics experiments and what we would like to know. So generally the things at these multi-purpose experiments that we want to measure are things like particle type, things like the form momentum and the position of origin of a particle. So for example, you might want to know if a particle originates very close to the beam pipe down here or way far outside of the detector, depending on the type of physics process that you want to measure. You might want to know the charge of the particle so that you can differentiate between particles and antiparticles. And maybe you might want to know the time of flight. So you could know that a particle really was in time with your physics collision and not out of time from some background process. So what I want to emphasize is that an integrated system of detectors is required to achieve this. Each technology has strengths and weaknesses. There is no detector that can do it all. You need to selectively choose different technologies to complement one another. And nowadays, nuclear and high energy physics experiments are designed around common features as they have very common event reconstruction goals. In general, if you're building a multi-purpose detector, you want to measure all of these particles that come out of this collision so that physicists can do whatever kind of measurement they're interested in with that. So here's some concrete examples, and you'll notice a lot of similarities between all of these designs, I think emphasized by this point. This is the CMS experiment, the EPIC experiment, the SPHENIX experiment, and the ATLAS experiment. And they have many common features amongst them with some differences that are tailored for the particular physics goals that each experiment is trying to achieve. So some commonalities are that you get as much coverage as possible, again, within these cost and space constraints that you might have, as you might want to measure all the particles from the interaction so that you really know I have some collision and this is everything that came out of that collision. That might help me understand whatever physics process I'm interested in. You probably also want to have a wide variety of technologies, again, utilizing these strengths and weaknesses. So maybe you have some tracking, some calorimetry, some particle identification, so that you get precise resolution of things like the momentum of particles, the energy of particles, and again, maybe their position of closest approach. Another thing that I'd like to emphasize, which I think probably was also already emphasized in the DAC talks last week, is that you might also want to take advantage of the extremely high rates that accelerator facilities can now provide. At facilities like RIC, where collisions happen on the order of megahertz, so billions per second, and at LHC, where they happen at tens of megahertz, there's an enormous flood of data that you are receiving. And you, as the scientists, the engineers, whoever that are working to build this experiment, you need to decide how to process that data. Maybe it's literally impossible to collect everything because you would fill up so many exabytes of hard drive space that you cannot afford to collect all the data. So you have to make choices about what kind of events you trigger on. Maybe you can collect all of the data, but there are computational consequences of that. That mean you have to design your physics experiments computing pipeline accordingly. So these are important considerations as well. And almost all of the experiments, or actually all of the experiments in the previous slide and many of these general purpose facilities now have extremely high rates where these kinds of things need to be considered. Okay, so how do we measure particles in an experiment? So if there is one thing that I would like you to take away from today's talk, it is this point right here. So all measurement techniques are basically based on the same very general principle, and that is you amplify and read out a signal that is measured from the particle's interaction with some matter. So some particle traverses some matter, it creates a signal, and then as your experimental apparatus, the goal of that is to amplify that signal to the point where you can actually detect it and have some measurement. So it is therefore important to understand how particles interact with matter, because that is our only way of actually detecting things. So this, I'm sure you've seen already this week, is the beta block equation for the beta block distribution for muons on copper as a function of the muon momentum. And what I would like to highlight is this point here, which is the minimum ionization point for muons in this case, which is at about a couple of hundred MeV. And this is where the minimum amount of energy that are required to actually start for the muon to ionize things in ionize the atoms in copper. And what's interesting that you'll notice is that excluding this radiative loss tail here, this is more or less, notice the log scale on the y-axis, this is more or less flat out to about 100 GeV or so. So once you reach this minimum ionizing threshold, you can be confident that your muon is ionizing your atoms and that you can maybe amplify some electrons that are liberated to measure some signal. So the beta block equation, it was developed by Hans Bethe almost 100 years ago now. And this describes the energy loss of a heavy charged particle for a particle with some charge and velocity. So this is a plot showing the distribution of the beta block equation for several materials, again, as a function of muon, pion, and proton momentum. This comes from the PDG. If you have time over, in the evening or whatever, you need some reading material, I strongly suggest that you go read the PDG, I think it's chapter 34 in the latest version. It's a super useful resource that will tell you all sorts of information about how particles interact with matter. So this is you can think about that as maybe some homework, or when you're traveling back to wherever you're from next week, download the PDG chapter for reading while you're on your flight or train or whatever. So this is valid for beta gamma between these values, about 0.1 to 1,000 within a few percent. And then outside of this, other effects become important. But the point to emphasize here is that we know this to within a few percent. So we can model, for example, in Geon simulations, how particles interact with matter quite well now. Okay, so now let's talk about electrons and positrons. Electrons are light, so they lose energy faster and scatter at larger angles. And you can think about this just with simple F equals ma. For lighter mass, you have more acceleration for the same force. And electrons also lose energy via Bremsstrahlung because they are an accelerated charge. So electrons and positrons, I use those synonymously. What term dominates in terms of the Bremsstrahlung versus the collisional energy loss depends on the incident particle energy. So this ratio goes something like the kinetic energy times some material dependent property. So the higher the kinetic energy, for very large kinetic energies, this Bremsstrahlung term is dominant. And as you get to smaller kinetic energies, then the collisional term becomes more relevant. And so we can look at this in conjunction with photon interactions. So for photons, they can interact via three methods with our material. Three interactions: photoelectric effect, which is the absorption of a photon; Compton scattering, which is the scattering of a photon; and then pair production, which is where a photon splits into an E plus E minus pair. So when you think about these three processes, what happens is that an interacting photon or electron rapidly leads to a cascade of electromagnetic particles, which gives us the concept of a radiation length. And I should have mentioned this a minute ago, but again, this plot just shows where each of these processes for photons is dominant as a function of the incident photon energy. And you see exactly what I was just sort of referring to, that at very high energies above about 10 MeV or so, pair production is dominant, so photons splitting into E plus E minus pairs. And then at sort of moderate energies around N MeV or so, you have the Compton scattering process that's dominant, and then below that you have the photoabsorption. So what happens with this cascade of electromagnetic particles leads us to the concept of a radiation length. And you can draw sort of a cartoon. Maybe you have some shower that looks like this, where you have a photon that splits into a electron-positron pair. Maybe these radiate some photons, and maybe one of these photons splits into an E plus E minus pair, and so on and so forth. You can imagine this goes way off the board over here. So you get this cascade of electromagnetic particles, and this gives us the concept of a radiation length. So the radiation length is defined as the average distance a high energy electron loses all but 1/e of its energy, some material. So the radiation length is only material dependent. It goes like something like this. And it is, again, defined for a given material. So if you pick copper, it has some radiation length. If you pick lead or whatever, it has some radiation length. And this will tell you how much material you need to actually stop your shower. So this is the entire principle behind calorimeters. The basic idea is that calorimeters use material interactions to stop high energy particles. That's it. Typically, they are built of high density materials because the more dense material you have, the more interactions you'll have, and so you have a more contained shower. And then this cascade of electromagnetic particles is collected and read out to determine the energy of the incident particle. So there are generally two types of calorimeters that we talk about: electromagnetic calorimeters, which are for which measure photons and electrons and positrons, and then a hadronic calorimeter, which measures hadrons. Again, this is a plot of the stopping power as a function of incident energy for electrons and positrons from the PEG. And again, you can see that this bremsstrahlung, after about 10 MeV, bremsstrahlung here dominates. And then there are contributions from other scattering processes below. But again, strongly emphasize, go read the PEG chapter. It's very useful. Okay, so what does this actually look like? Since pictures are worth 1,000 words. So this is an example of an 8 GeV electron, this orange line here, that is incident on a scintillating fiber tungsten electromagnetic calorimeter. So this is a simulation, and I think it very nicely shows what kind of multiplicities we're dealing with in a shower. So this one 8 GeV electron is incident on the calorimeter face, and then you can see this produces this shower of all these photons and electron and positron pairs that radiate, that lead to other particles, and eventually out the back of the calorimeter here we lose some. So we'll talk about that a little bit later. But you can see that there are many, many, many particles that are produced from this shower. And the idea behind a calorimeter is that you want to put enough material here to collect all of these particles so that you can determine this incident electron's energy. Okay, so let's talk about the resolution of calorimeters. So just as a reminder, the radiation length is only dependent on the material. So if you do some calculations with that equation I showed before, typically for a 99% containment of the shower, you need something like 20 radiation lengths. Depends on the material, of course. It might be less, it might be a little bit more, but it's sort of in that ballpark that you need to contain the shower. So what I'd like to emphasize is that in a perfect calorimeter, the resolution depends only on the number of particles produced in the shower. Of course, your shower has some statistical fluctuations because not every shower develops the same. Maybe since you can imagine there are so many particles that are produced, you may have different combinations of electrons, positrons, and photons that you need to collect. So in a perfect calorimeter, the resolution depends only on the number of particles that are produced in that shower. And this is the 1 over square root of E term. This is called the stochastic term, and is really just related to intrinsic shower fluctuations of the particular material or build of your calorimeter. Of course, reality is never perfect, so you have other terms that are relevant in your resolution, like this constant term, which comes about due to inhomogeneities in your calorimeter. Maybe you have some boundaries where you don't have you're missing readout electronics or something like that, so you have some light that escapes. This would be considered energy leakage. These kinds of effects go into this constant term. And then there's a third term that is related to noise, like readout electronic noise. And this goes as 1 over E. So just as a concrete example of what this looks like, this is a plot of the S-Phoenix EM-Cal from a test beam that was performed 6 years ago now. On this left plot shows is the energy linearity. So what this shows is the input energy from some test beam where we took some electron with known energy and shot it into our calorimeter. And then the reconstructed energy is on the y-axis. So in a perfect world, this would be an exactly linear function. Whatever you put in is exactly what you measure out. And you can see from these fits here that is mostly true. There is an E squared term that we use to identify how nonlinear this system actually is. And then on the right is a plot of the energy resolution. So this is again as a function of the input energy of the electron. This tells us the width of the distribution that we actually measure in the calorimeter. And if you look carefully on your computer or something, it's probably hard to read in the back from on these slides, but you'll see that there are exactly the terms that I was referencing. There's this 2% term, which is related to the momentum spread of the beam. So that's the uncertainty in the incident energy. And then there's this constant term and stochastic term, where we found that the noise term was small enough that we could neglect it in this particular example. Okay, so let's change gears a little bit. Oh yeah, please raise your hands and ask questions if you have a question.
Yes, can I ask question in your last slide? If I look at the plot on the left, at the bottom here, as you go to higher energy, your agreement, like, so it's a further away from one at the bottom, right?
Right.
Is that physics, or is it just like you know less about the beam at higher energy?
So that is because the energy leakage is higher at higher energies. So your shower produces more particles. And because of that, we lose more energy out various sides of the calorimeter. So this is a real calorimeter, so it definitely has defects and things that are not perfect about it. Another thing to consider, which I think will be more relevant in our discussion tomorrow, is that this also depends on how you put together the energy in your calorimeter. So something to keep in mind is that, we talked about material interactions, and you have some particle that liberates some electrons or something, that you read that out. That doesn't tell you anything about the particle. It just tells you that you had a pulse in like an oscilloscope or something like this. You need to take that and somehow manipulate or massage the data such that it tells you something about the incident particle. And there are inefficiencies and things like that depending on what kind of algorithms you choose. So we'll talk more about that tomorrow, but related to this, we use an extremely simplistic algorithm to reconstruct the energy, which maybe you could think of something fancier or more complex that might do a better job. So hopefully that answers your question. Okay, so let's switch gears a little bit and go back to our discussion about material interactions and talk about Rutherford scattering. So particles can also undergo Rutherford scattering, where there is some scattering from an atomic nucleus. And how this manifests itself is by deflecting the particle's direction through many small angle scatters. So the cartoon from the PDG is shown here, where you have some particle that's incident on some material, and it maybe undergoes some small angle scatters that are represented by this characteristic angle here called theta plane. And the width of this angle is given by this equation here, which is directly dependent on the thickness of the material and radiation lengths. So what that means is that the smaller the thickness of your material is, the fewer scatters that you have, and therefore you'll have a better measurement of your particle trajectory because you won't have so many deflections. So this is now related to the tracking side of things. So let's talk about tracking. How do we actually reconstruct tracks in experiments? Very simply with F equals Q V cross B. So this is, from your basic introduction, physics introduction classes. As an exercise, I would encourage you to try to derive this for yourself. So based on the curvature of a track or a particle in a magnetic field, you can calculate its transverse momentum, which is equal to 0.3, which is some constant value, times the field strength, the magnetic field strength in Tesla, times the radius of curvature of the particle in meters. So what we need to do in order to determine the tracks is measure the sagitta or radius of curvature to provide the momentum, and that gives us an estimate of the particle's free momentum. So for precise measurements of tracks, you need three things that sort of compete against one another. You need a large magnetic field so that the particles bend even more, and thus you can see much better their radius of curvature. You need a long lever arm. For example, in this cartoon here, if you only made some measurements, at the very beginning of this radius of curvature here, you might not get as accurate estimate of how the particle is bending in the field. And then ideally, you want many measurements along the trajectory so that, again, you can measure out this whole curvature. However, this is where now this multiple scattering term from the previous slide comes into play, because this scales with the amount of material that's traversed. So you need to, there's an optimization problem here where you need to have as many measurements as possible, but with as little material as possible over as long a distance as possible. So you have to give and take between those things because they kind of compete against each other. The momentum resolution goes as something like 1/BL squared. So the momentum, so again, the larger the momentum field, the smaller your resolution, and especially this lever arm, this length term L, since it's squared, the longer your lever arm, the lower your momentum resolution is going to be. But again, this competes with the multiple scattering. So the momentum resolution of some experiment looks something like this. You have a constant term that is from multiple scattering. So you want to limit this as much as possible because that's really the baseline of your resolution. And then you have some linear term that's dependent on your measurement uncertainties. Again, we'll talk a little bit about this tomorrow, but when you read out some signal, that is an estimate of the location of a particle at one fixed place. There is some uncertainty to how well you can actually measure that. So you need to consider, so that factors into your overall track momentum resolution. So tracking optimization is a tricky problem where you need to optimize the path length and number of measurements on a trajectory while minimizing the total material that's traversed so that this entire distribution is sort of as low as possible or as low as needed for your physics measurements. So here's an example from EPIC from the main experiment of the EIC. This shows the momentum resolution as a percentage as a function of the true input pion momentum in some simulation. And so if you look really carefully at this plot, you can see at very low momentum, it's nearly flat, where this multiple scattering term dominates. And then as you get to higher momentum, where the measurement uncertainties begin to dominate, this becomes more linear, and it gradually increases to about 1% at something like 15 or 16 GeV in rapidity in this case. Okay, so now we know the processes by which radiation and matter interact. So how do we use it to detect other radiation, other particles from our process? So as a reminder, what did we actually want to measure? We wanted to measure something like the forward momentum and the charge of the particle. So we need two things that complement one another. We need first detectors that interact very little with the particle, but enough to measure a signal so that we can determine their trajectories. So this is the tracking detectors. And then we need detectors that can stop a particle completely and measure the deposited energy. That is what the role of the calorimeters are. So these are kind of opposite in the sense that they give us different information via different methods. One, you want to interact with the particle as little as possible. One, you want to maximally interact with the particle to get the momentum and energy information. Okay, so the rest of this lecture is going to be dedicated to talking about different kinds of calorimeter and tracking detector technologies, some of which are relevant to the EIC, some of which are not, but are relevant to other physics experiments around the world. And I think it's useful to have a sort of comprehensive knowledge about different technologies, what their advantages and disadvantages are, and things like this. So the first couple of things that we'll talk about are electromagnetic calorimeters. And the first type are called sampling calorimeters. So sampling calorimeters are called this because there are different materials that do the sampling, which provides the signal that you actually measure, and absorbing, which is the dense material to absorb or degrade the particle energy. So one example of this is scintillating fiber, or sort of colloquially called spaghetti calorimeters. And this is the S-Phoenix electromagnetic calorimeter. If you pull up these slides on your computer and you zoom in really closely to this front face of the calorimeter, you'll see a bunch of little dots. And these are actually fibers that extend throughout the Z length of this calorimeter. The rest of the calorimeter is composed of a tungsten epoxy mix powder. And so in this particular case, for spaghetti or scintillating fiber calorimeters, you have some absorber that exists sort of throughout the calorimeter, and then you have some fibers that are the sampling part that collect the light and send the light down to some readout mechanism like a silicon photomultiplier or something like this. So this is one case, but there are other spaghetti calorimeters that have been built. So in this particular instance, you have a light guide here, which actually guides the light from the scintillating fibers out to some readout electronics here, so that you can actually measure the signal. So sampling calorimeters have an important concept, and that is the sampling fraction. And not very originally named, the sampling fraction is maybe exactly what you'd expect it is. It's the fraction of energy that you actually sample from the shower. So the way that this is defined is the energy for some MIP that's in the sampling or the active part divided by the total energy deposited. And you can then determine what your measured energy is based on the energy that you actually sample in the calorimeter divided by the sampling fraction. That tells you something about the input particle's energy. And this is true for all sampling calorimeters. Yeah.
How do you know what fraction you've sampled if some particles go out the back, for example?
So that's a good question. You have to measure. So you can measure it in test beam type scenarios and then also compare to simulation, because ultimately you don't know in a test beam how much energy goes out the back. So what you want to do is build your calorimeter and develop a model of it that is accurate enough such that you can prove to yourself that you understand the way that showers develop in simulation, where you can actually know the truth. But ultimately you are right. If you were to just build a calorimeter and shoot an electron into it, unless you have some knowledge of the input energy, you don't know necessarily what kind of energy is leaked out. In test beam situations, you usually do know the input electron energy or whatever particle energy, because the accelerator physicist can tune the beam to be some particular input energy. But in a real physics experiment, you don't know the input energy. So you have to determine this with a collection of data that you collect, maybe in a more controlled environment like a test beam, as well as some simulation. Okay, another type of sampling calorimeter is a sandwich or shashlik sampling calorimeter. These are also common and have been built in lots of different experiments. These have a similar sort of principle, but instead of having fibers that extend throughout the length of the absorber, you just have sort of plates or some interwoven materials that oscillate. So in the case of the Atlas calorimeter, there's the Atlas, I think, barrel calorimeter is a liquid argon calorimeter that has some honeycomb plates that are used as the sampling part, or the argon is the sampling, and there are some other heavy plates that are used as the absorber. Whereas, for example, the Shashlik EM-Cal at Hera B has these large plates that are interspaced between, or that swap between scintillator tiles and absorbers. So typically you have some heavy absorber like lead, tungsten, or copper that's interleaved with some plate of scintillator like plastic or crystal. And then you read these out in some way, like for example, with this Shashlik EM-Cal from Hera B, you have a photomultiplier that is connected to some presumably fibers or something like this that read the light out to the photomultiplier. Yeah.
On the last slide, why do you define the sampling fraction using bits?
Because that is the most controlled situation where you have a particle that you know is ionizing the material. So if you go back to our beta block equation, that's basically where the stopping power is effectively flat. So it's a more controlled environment where you know you have some input energy and you start ionizing particles at this whatever couple hundreds of.
Okay. Is it always just using like muons? Because I've seen it with like you just find it with electrons too.
Yeah, you don't have to.
Okay.
Muons are just typically the prototype example because they interact least since they're heavy leptons, and we have them abundantly from cosmic rays. So typically people do calibrations with cosmic muons to the extent that they can. And those are the sort of easiest thing to understand because they interact the least. Okay, another type of electromagnetic calorimeter is a homogeneous calorimeter. So homogeneous calorimeters are basically the opposite of sampling calorimeters in that they use the same material as the absorber and the sampler. So instead of the sampling calorimeter, which has some like plates or something that are spaced apart, the homogeneous calorimeter has the same material that acts as both. So an example of this is the CMS lead tungstate crystal calorimeter, barrel EM-Cal. And I'd like to highlight the pros and cons of both of these here because, again, they have different trade-offs. So homogeneous calorimeters give you the best energy resolution because you have the same material that's doing the sampling and absorbing. So that means you sample the entire shower. Your sampling fraction is effectively 100%. The downside to that is that it's expensive. So you have to trade off a little bit. Sampling calorimeters are generally cheaper. They can be more compact. And in general, they're sort of more customizable because you can choose different materials for both the absorber and the sampler. But you have the downside that only a fraction of the shower is captured. So your energy resolution is going to be limited by how much of that shower you actually sample. Okay, let's go to hadronic calorimeters now. So hadronic calorimeters are a little more complicated because hadrons interact with nuclei and create both an electromagnetic and hadronic cascade. So a hadron might interact with some nucleus and produce some hadrons, but it might also produce some pi zeros, which very quickly decay into 2 photons. And if you create some photons, then those photons will, if they're high enough energy, they will pair produce, they will create E plus E minus pairs that will have bremsstrahlung and so on and so forth. So hadronic showers are more complicated because they have both a hadronic and an electromagnetic component. So shower development in hadronic calorimeters scales with the nuclear absorption length. This is basically an analogous concept to the radiation length, the EM-Cal, but is relevant for the hadronic component. And these need to be, in general, much, much thicker to capture the full shower development. And to see this in action, I think these are 2 great pictures which show this. This top picture is a 100 GeV electron that is incident on some iron electromagnetic calorimeter. Again, you see this shower develop. You see all these electromagnetic particles spray and create some shower. And then this shows a 100 GeV pion that's incident on some iron hadronic calorimeter. And you can see that the hadronic shower extends to 150 centimeters, whereas the electromagnetic shower goes maybe 30, 40 centimeters. So it's something like a factor of 3 to 5 longer in this particular case that the shower needs to be fully captured. Another example is from that you can compare to the 8 GeV electron shower that I showed earlier in the S-Phoenix EM-Cal is this 32 GeV pion. Again, this was in a sort of test beam type setup that's incident on the full S-Phoenix calorimeter system. This pion actually happens to start showering in the EM-Cal, but the shower develops all the way through this entire region here, which this doesn't have a length scale on this picture, but this is an order a meter that spans the entire thing. So again, the point of this is to highlight that hadronic showers are significantly more complicated because you can have more types of interactions and you need a much thicker material to actually fully capture the shower. So because of this, fluctuations of the shower development are much larger, which inherently limits your energy resolution capabilities. If you remember from some slides ago, I don't know how many now, I mentioned that the stochastic term is basically entirely dependent on the fluctuations of the shower development. So if you go back a page, you can see that in these types of showers, you could have huge fluctuations that would be very non-trivial to even model, let alone to fully capture. So in general, our stochastic term is much larger in hadronic calorimeters than it is in electromagnetic calorimeters of order like 50% or even larger. 50% is quite good for a hadronic calorimeter. So you can see this again in this S-Phoenix test beam type scenario. This plot on the left again shows the energy linearity, and the plot on the right shows the energy resolution for both electrons and hadrons in the H-Cal. And in particular, what I want to highlight two things. The first thing is that you can actually measure electrons in the HCal, and they have a much better resolution than the hadrons in the HCal. And that is because electrons still produce electromagnetic showers, and an HCal still needs to be able to measure this light because hadronic showers can produce an electromagnetic component. And since the electromagnetic shower is much more contained, much more understood, you get a much smaller stochastic term. While if you look carefully here, the constant term for electrons in the HCal is about the same as the hadrons in the HCal. The big difference is in the stochastic term here, where there's a difference of about 50 percentage points. So that's, again, a result of the hadronic showers being much more complex. So nonetheless, I think it's important to emphasize that even at EIC collisions, which are in general lower center of mass energy, but like the LHC or something like this, the neutral component of jets is extremely important. This is some Pythia simulation that I ran a couple of years ago for the highest EIC energies of 18 GeV electrons on 275 GeV protons. And if you just naively sort of run a jet finding algorithm over the information from the Monte Carlo, you can plot the number of constituents in the jet that are charged hadrons, neutral hadrons, and photons. And in general, there's this flat contribution as a function of PT that's about 1 neutral hadron per jet. So if you have especially EIC energies, if you have a jet that only has 3, 4, or 5 particles or something like this, and one of them happens to be a neutral hadron, you will be missing a substantial fraction of the shower or the total jet energy by just missing the neutral hadron completely, which is not having an HCal at all. So I think it's important to emphasize that even though HCals are more complicated, they serve a very important role depending on where your phase space requires them. Okay, so I'd like to mention one more thing about calorimeters, and that's sort of next generation calorimeters. Next generation calorimeters sort of combine the EMCal and HCal technologies for 3D or even 4 or 5D shower development. So this would be measuring like energy, time, and position of the full shower development. And for example, at CMS, they're building this high granularity HCal, doing lots of R&D on this for the high luminosity LHC, where they will be swamped with backgrounds. So having some timing information is extremely important so that they can identify if a particular shower was in time with a physics collision or out of time, maybe due to some background or something like this. So the HGHCal has 28 layers of tungsten copper plates with some silicon sensors for the sort of EMCal component, and then 12 layers of brass and copper plates with some silicon sensors for the HCal component. And I'm not personally an expert in the HGHCal, but what I want to highlight, which I think is quite phenomenal, is the large number of channels that are required for this precise shower development determination. So the number of channels in your detector is effectively directly related to how precisely you'll be able to measure the output shower or something, whatever you're measuring. And the HGHCal has 6 million channels versus the SPHENIX EMCal and HCal, which has 28,000. This is 2 orders of magnitude larger in terms of channel count, which really tells you how complex of a machine it will be and how much more precise it is than some other calorimeters that are on the market. Okay, so that wraps up my calorimeter portion. So now let's change gears to tracking detectors. So again, something that I want to emphasize is that tracking detectors all operate under effectively the same principle. Some particle liberates some charge that is read out to determine the position of that charge. And as a reminder, we need to limit the material interactions as much as possible. So we want to get in the way of the particle enough, but just enough, nothing more. So tracking detector, I always like to try to make things sort of relevant to things that you have seen before. Tracking detector is kind of like a cloud chamber. You look at a cloud chamber, you have some radiation that's coming off, and you can see from the condensation where the track actually goes. Tracking detector is basically the same kind of principle, but spoiler, it's much more complicated than a cloud chamber, which we'll talk about. So let's talk about ionization and avalanche. So again, the basic principle is that you have some path of an ionizing particle that traverses some material. It liberates some electrons, and those electrons drift in some electric field or something like this, some boundary where they then are avalanched to the point where you can actually read out the signal of the electron. And based on where that avalanche is collected at some anode wire, for example, that can give you some information about where the original electron was actually produced. So all the detectors have the same basic idea. Particle liberates electrons, these electrons avalanche, and then the position is determined from this information. And how you do that can vary from detector to detector. So this exact example is the basic principle behind the wire chamber, where you have some particle that traverses some gas and liberates some electrons from these gas, and then these electrons drift to these anode wires, which are then read out to determine the position. Generally, drift and wire chambers give you position and drift timing information that provides something like order 100 micron hit resolutions. So this is really precise information that we can measure these particles to of order 100 microns. There's also time projection chambers, which again operate under the same principle. Time projection chamber, this sort of cartoon, you have a particle that liberates some electrons in a gas. And instead of the electrons drifting to an anode wire, they drift to some plane here at the very end of the detector and are then read out there. So you get some XY information of the electrons that are liberated from, for example, these little red dots here. And then you can determine the Z position based on how long the electrons drift in this electric field. Generally, the positive voltage is the central membrane here at the middle, and then you have some negative voltages applied at the readout plane, such that the electrons drift that way. So something to keep in mind about time projection chambers or TPCs is that they have a very long drift compared to wire chambers, because you have to drift over. If you look at the size of this is a meter. So your electrons are drifting something like a meter. And in the case of S-Phoenix TPC, which is shown here, that drift time is like 14 microseconds. So it's a significant amount of time when you consider things like the rate of the Rick accelerator, which collides bunches of protons or ions on the order of 100 nanoseconds. So TPCs are generally subject to a lot of background and pileup that you have to sift through because of their long readout times. So here's an example that, again, I think really nicely shows that these are just like cloud chambers. These are event displays from S-Phoenix, which show the tracks that are measured in real collisions. And you can see these, it literally looks like some radiation, just made some condensation up here or something like this. So this is, I think, a great analogy. Okay, another thing that you'll commonly hear about or read about is GEMS, gas electron multipliers, are a type of avalanche technology that helps to amplify the signals. So GEMS use thin holes that are created in regular patterns to amplify signals, and then some electric field is put across these so that the field is extremely small in the hole, and that the electrons create these avalanches in much stronger amplifications. So typically layers of GEMS provide high gain readout. And another really nice thing, which is why they are so commonly used in the field, is that they can be mass produced for relatively cheaply. So that makes them very, very useful technologies. They are used at Compass, STAR, S-Phoenix, and I'm sure many other places, as CERN mass produces these now for many different experiments. So these are a great technology for readout. So there's also silicon detectors. Silicon detectors are probably the most exciting of tracking detectors, in the sense of they provide the smallest amount of material and the highest hit resolutions that we have right now as sort of detector technologies on the market. So silicon detectors have the sensor and readout electronics integrated onto some single chip, where in this, again, cartoon, you have some particle that traverses this active layer, liberates some electrons, and these drift to a diode, which are then amplified and read out on this chip. Silicon detectors can provide extremely high precision. So we're talking order of microns or tens of microns hit resolution, which is quite phenomenal. And there are generally two types. There are pixel silicon detectors, which provide you information in 2 dimensions, or there are strip silicon detectors, which provide you information in 1 direction. So there's a strip direction that has a very large resolution, typically of order of a millimeter or something like this. And then in the strip detector, you have the other pitch, which actually gives you order tens of microns resolution. So the really great thing about these silicon devices, which you'll hear a lot about, MAPS detectors, MAPS are monolithic active pixel devices. They have extremely small material thicknesses. So there's something right now like of order 0.1% radiation lengths per layer, which includes all of the sensor readouts and cooling, all these other mechanical things that you may not think about, but that are important engineering concerns. So this is quite phenomenal. And the people who actually do a lot of the silicon hardware development are even trying to push this further, something like 0.05 radiation lengths per layer for the EPIC experiment and for the next generation of ITS and MAPS technology. So some examples are the MVTX and SPHENIX, which is shown here, and the ITS, which was the first real development of these MAP sensors, which is at the ELISE experiment. These are the outer layers, I believe, of the ITS. And something that I like to highlight about these silicon detectors is that we typically think of these particle physics experiments as being huge. If you look very carefully at these pictures, this is someone's hand. So this MVTX is like 2 hand lengths long. It's extremely, extremely small, where each of these layers is at something of order a couple of centimeters from the nominal origin of the experiment. The ITS here, these are the outer layers of the ITS, which you can see are sort of the size of half of a average person, but there are even smaller layers that are not shown in this picture that go inside here. So the reason that these are so small, unlike calorimeters, for example, is that, again, you want the material thickness to be small, but silicon detectors also have a very large channel count, which means they're extremely expensive. So you want to make your silicon detector as close to the beam pipe as possible for a couple of reasons. That limits the amount of surface area that you need to buy, so it makes it cheaper. But there's real physics motivation, and that is that these high precision resolution measurements that you can get from silicon detectors provide you very good pointing resolution for charged particles. So you can know to order tens of microns exactly where this particle came from. And that allows you to do things like identify heavy flavor decays that maybe have a longer decay length. Okay, so the last thing that I will talk about is MPGDs, micropattern gaseous detector. Detectors are a further evolution of wire chambers. So this is a very similar kind of image. And if you look carefully at this, it's kind of like a mini TPC that's compact, it's smushed into a really small layer. So you have a drift electrode here, and then you have some anode electrode here, such that you have an electric field, and you have some particle that traverses, typically gas, liberates some electrons. Again, they drift to this micro mesh and are then avalanched and read out. And what's important to emphasize for the MPGDs is this is a schematic diagram for the teapot, which is a micromegas detector. It's a type of MPGD, but notice the scale here. This is 3 millimeters, and then something like 100 or so microns of this amplification gap. So these are extremely thin detectors where the gas is, both where the gas is and where the amplification region is, again, to limit your material interaction and also get as much amplification as you can of the signals that you don't miss these avalanches. The other nice thing about MPGDs is that because there are small distances in this amplification gap, this limits space charge accumulation. So something that I've completely ignored that if you were paying attention very carefully, you would have thought about, is that every time we liberate electrons from this gas, that leaves some ions. And ions are charged, so they will drift in this electric field. What happens is that you have streams of electrons drifting in one direction, streams of ions drifting in the other direction towards the positive electrode. And these positive charges can create distortions of your signal for other tracks that are coming through your detector. So it's important when you're designing or talking about tracking detectors that you want to try to limit these space charge accumulations as much as possible, as these distort your signals and will degrade your bit resolution. Okay, so there's lots more stuff that exists. I'm sure every lecturer has said this, that you only have time to scratch the surface of this field in an hour. However, I picked these as they mostly cover the technologies that are being used in a lot of experiments and have been used in past experiments or are planned to be used in current or future nuclear and high energy physics experiments. A lot of technologies like sampling calorimeters have been around for a long time, and they have been because they're super versatile and can be used in lots of different ways. So let's return to our cartoon. The important point to take, this is a transverse slice of the CMS detector, is that we want to have silicon detectors or tracking detectors first that cover as much distance as possible, but limit our material interactions as much as possible so that the particle trajectory is not modified significantly. Then we have electromagnetic calorimeters, such that we stop electrons, positrons, and photons. Then we have hadronic calorimeters, such that we stop any hadrons and measure their energies. And then in the CMS experiment, you also have muon chambers because heavy leptons survive. They don't have, because they're heavy, unlike electrons, their rate of pressure along is much smaller. So they interact electroweakly, not hadronically. So muon chambers are often built at the very outsides of experiments because of this. Okay, so again, this only scratches the surface. The field is full of very creative and hardworking people that are excited about the next breakthrough. Things like MPGDs were only really developed in the last 20 or 25 years. And they're really now just becoming to be, I think, used more ubiquitously. Because of course, when someone develops this technology, they didn't just mass produce a giant detector out of it. They built, some small test sample to prove the technology. Something that's important to think about is that when you build a particle physics experiment, you have to be able to mass produce some of these technologies. So can't necessarily develop some R&D thing and then expect to have it mass produced in a couple of years. So we've only discussed some detector technologies that are used in modern nuclear and HEP experiments. And something that I want to emphasize in preparation for the lecture tomorrow is that all I have told you right now is about some detectors that measure only signals of a particle. So this is something like on your oscilloscope, a pulse or a waveform or something like this. I hope that you are asking, how the heck do you turn this into a physics event or something that we can even make sense out of to do some physics analysis? And that will be the goal of tomorrow's lecture, is to discuss how we take this data and actually transform it into something that is that makes sense. So, okay, thanks everyone.
Thank you. And yeah, we have time for questions. And again, we'll have the evening session. So anything right now? Go ahead.
You're hungry for lunch?
Ask what is there.
Sure.
Yeah, so you mentioned some EM color using sampling is a sampling calorimeter. Do you know roughly what's the sampling fraction for those cases for EM color?
That's a good question. So I don't know the sampling fractions for the Atlas liquid argon and the Shakespeare calorimeter that was used at Harrah-B, but for the S-Phoenix calorimeter, since that's what I'm most familiar with, it's of order a couple of percent.
That's similar to CMS.
Yeah.
Each color, but I'm wondering about.
Yeah, so again, it depends on what kind of technology you use, of course, but for the S-Phoenix EM cal, at least it's something like 2, 3, 4%.
Okay, I see. Okay. Thank you.
Any other questions? All right, if not, let's thank Joe again. So it's 11:30. We'll break for lunch and we'll gather again at 1 o'clock. So that'll give you 90 minutes for lunch. And we'll see you back here. Thank you.
Nothing wrong with it.